algorithm. And the algorithm, specific algorithm that you need to go for is the Bell-Mansford equation or dynamic program-based structure. And here, the basic notations that you come across, one of it is capital D y of x, basically cost of sending a data from x to y. So least cost of sending a data from x to y is definitely one. Now, based on Bell-Mansford equation, you're going to compute what is the least cost set of path, the least cost of sending a data from x to y. That is minimum across all the neighbors that you're going to consider of a particular node. So the cost of that, the cost of sending a data from x to that particular node and from that particular node to the destination. So if there are n such adjacent nodes, so we have to compute what is the cost for all those, and from those, what is the minimum, and that we are going to take it as the concept. So just to get a glimpse of what we just mentioned, so just say that you want to send some data from V to Z. So V to Z has a different path, but manually looking into that, what you can see is that this is one least cost that you can see. There are other paths, but this is the least cost. So 2 plus 1, that is 3 plus 2, that is 5. So that is what is the least cost of sending a data from the node V to Z is 5. Now, if you consider X, there are different nodes, but this is the least cost that you can see. That is 1, 2, that is 3. So D of X is said is basically 3. And from W, what you can see is that the least cost is this. So basically, the cost of least cost of sending a data from W to Z is basically 3. So what do you mean by the Bell-Mansford equation? So Bell-Mansford equation says that you want to compute what is the least cost of sending your data from U to Z. So when you compute that, what you have to see is you have to find out what are the different neighbors of Z. So one neighbor is this, that is V. The second neighbor is X. You can say you can reach here, and the third neighbor is W. So this is what you want to reach. So what does Bell-Mansford equation say? So Bell-Mansford equation says that you can compute what is the minimum cost of sending a data from U to Z. That is minimum across all the neighbors of U. And what are the neighbors of U? V is one neighbor, X is another neighbor, and W is the another neighbor. So the first part of it is cost of sending a data from U to V. And once you have your data from V, you have already computed what is the cost of sending your data from V to Z. So that is what you write. So you send your data to V and then least cost of sending your data from V to Z. Or else you can send your data to X. And then you have already computed what is the least cost of sending your data from X to Z. So send your data to X and then add it to the least cost. Or else you can send it to W. You can send it to W and then from there to Z we have already computed. So you have this. Now out of this, which is the minimum? One thing is from you're considering V, what happens is that when you're considering V, you're sending it to V, that is 2. And from V to Z, we have seen that it is 5. So there is basically 2 plus 5. Now, if it is X, is saying from U to X is 1, and from X to Z is basically 3. So 1 plus 3. Now, you're taking W, which is basically cost of that is sending is 5. And from W to Z that you already seen is 3. So that is 5 plus 3 is 8. So of these, the minimum is basically 1 plus 3. And that is what your new value would be. The minimum cost of sending your data from U to Z is basically 4. That is across all its neighbors. And this is what Bell-Mansford equation says and how we are going to compute your distance vector. And why you call it as distance vectors, then now you for each update, when you're going to share information, you're going to share the weight factors only. If there is any change, or if there is whatever it is, the weight factor, that 1, 3, 5, whatever it is, that cost that you have, that final value you're going to share. You're not going to share any other factors over here. So we have a lot of things coming over here. So when you're coming to a problem, so you have a graph like this. So if you have a graph like this, the number of nodes that comes over there is X, Y, and Z. Now, what you have is you have to compute this particular, you have to draw this particular, router table. In each of the routers, there will be a table like this. What does it say? It says that this column defines what is the from where it is originating and to where it is going. So this says it is from which side it is originating, and this side says to where it is going. So when you read that table, it says that you're sending your data from X to X, sending your data from X to Y, sending your data from X to Z. So second row says that sending your data from Y to X would be this, sending your data from Y to Y is this, Y to Z is this. So you have such tables or matrices in each of those routers that you're talking about. So this basically is the timeline that you're drawing. Okay. So basically what you have on your horizontal axis is your timeline. So if you want to just say that this is basically at t is equal to 0. At t is equal to 0, when you're considering node X, this is the table at node X. So at that time, you don't know anything about Y, you don't know anything about Z. So basically you're going to put infinity. In the case of node Y, you don't know anything about X and you don't know anything about Y. So you put all as infinity. In the terms of the node Y, Z, at time t is equal to 0, you don't know anything about Y, X and Y. So you put as infinity. And you put some values for that particular corresponding row from X to X, X to Y, and X to Z. One thing you should be noting is if you want to send something from a particular point to the same point, there will not be any link cost. Now you are starting from here and you are reaching here itself. There's no link cost, right? So you're going to put it as 0. Now again from this plot, what you can see, cost of sending your data from X to Y is 2. So that is what you have written. X to Y is 2 and X to Z, X to Z is 7. So you update that here. Now in terms of your router Y, Y to X, you're taking Y, okay? Y to X is 2 and Y to Z is 1. So Y to X is 2 and Y to Z is 1. And Y to Y is 0, we already said that. Now you're taking the case of Z here. Z to X is 7, right? So you have 7. And Z to Y is 1. So you have 1. And Z to Z is 0. Fine. So that would be at time t is equal to 0. Now what happens at time t is equal to 1? What you should be noting is that time t is equal to 1. All these nodes will be sharing its information. So what information does the router X gets? X gets information from router Y. That is what is being shown here. And it gets information from router Z also. So at this time, what happens is that it does not do anything. It just types in the values that it has got from Y. So from here you get 201, so you update it here. And from here you get 710, you update it here. Now what we do here in Bellman-Ford equation is that you're going to compute what will be based on these information, everything information. What will be the new Y and Z values from X to Y and X to Z. Okay. So with that, we need to update. So anyhow, you know that from X to X is 0. So if X to X is 0, you put it 0 here. Now X to Y. Now you say that for X to Y, you have to say that what would be the minimum across on all its neighbors. Okay. Minimum across all its neighbors. So what do you do? You're going to go from X to Y. So X to Y, one part you can have is you can send your data from X to Y. You can send your data from X to Y plus the cost of sending your data from Y to Y. Okay. Cost of sending your data from Y to Y there's no cost. So basically that is 0. Is that a minimum? Or else what you can do is that X can send it to Y, Z, and then Z can forward it to Y. So what you can do is X can send your data to Z, and then Z can forward that to Y. So these are the two neighbors that X has, and this is the cost associated. And numerically at all minimum across all the neighbors of X. So this would be what will be your new value of this particular thing would be, what are you going to compute basically? What is the cost of sending your data from X to Y is what you're going to compute. That is what your statement is. Now what is it? Minimum across this. First line says is this 2 plus 0 is that minimum, or else you can send from X to Z, that is 7 plus That is from Z to Y is basically 1. So you can see that this is minimum, right? So you're going to update this as 2 itself. Now you want to compute what is this. Now this you say that what is your cost of sending your data from X to Z. Now it is minimum across all the neighbors of X. What is it? So if X want to send something to Z, so the first you can go directly. So what is it then? You can send your data from X to Z plus cost of sending your data from Z to Z. That is one route that you have. The second route is that X can send it to Y. So you can send it to Y and then from it can forward that from Y to Z. So this is it. So which of these two are minimum? So if I write the numeric over here, minimum across all the neighbors of X, C of X comma Y, X comma Z is 7. 7 plus 0 is minimum, or you can send it to X and then Y can forward it. So basically 2 plus 1, that is basically 3. So 3 is minimum. So what you will write here is 3. This is for node X. Now, if you want to draw it for node Y, so this you have the same thing. So you have X, Y, and Z, X, Y, and Z. So what are you getting from node X? You're getting the values 0 to 7, and from node Z, you're getting the values 7, 1, 0. Any updated values only go to the next phase. Okay. And now we want to compute what your values of this particular row is. Because in which row which router you're standing, only that you want to compute. And whatever is being shared, you're just going to fill it. So what you know without computation is cost of sending a data from Y to Y is 0. This you can write as such. Now, based on Bellman's-Ford equation, what you can do is you have to compute what is the cost of sending your data from Y to X. So you write, what is the cost of sending your data from Y to X? Bellman's-Ford equations, minimum across all its neighbors of Y. Okay. Now from Y, you want to send it to X, right? So cost of sending your data from Y to X plus cost of sending your data from X to X. Is that minimum? Or else Y can send it to Z, right? So cost of sending your data from Y to Z plus least cost of sending your data from Z to X. So which is minimum? This is basically, if you write the numerics of it, minimum is cost of sending a data from Y to X is 2, 2 plus 0, or else the other one would be Y to Z is 1, 1 plus 7 would be 8. So this is your right as 2 itself. Okay. Now the next thing for Y to Z, Y to Z, again, you go with the same principle. That means you send your data to Z plus cost of sending your data from Z to Z, and then you can send it to X and then forward. So anyhow, you'll see that this is a minimum. So this is 201. The same thing you go with node Z also, and then you compute it. So we'll just So based on that, we see that this is the thing that we have computed, and we see that no, this is again what we have computed. We go on with Z also we compute. Now something extra points that you should be noting here is this is what we initially said that this we are going to do as t is equal to 0. This is basically t is equal to 1, and this is basically at t is equal to 2. And how many times should we go? What should be the stopping criteria? Now you see that no, at t is equal to 0, there were changes over here, right? So you do t is equal to 1. Again, you see that no, there is this particular change over here and this particular change over here. So this has been shared and it goes to iteration t is equal to 2. Now you see that no, even after computing everything, we do all the same process and we'd see that there's no changes here. All are fixed. There is no change comparing, so we stop it. That would be a stopping criteria. Let's assume that if any one of these values change, and just assume that if any of these values had changed, then you should be having to compute it once more, share it once more, and compute p is equal to 0. But that doesn't happen because why does it not happen? Because here what you see is that there is no change that is happening here. So they will never be t is equal to 3. we just stop it over here. Okay,